"Tell me and I will forget, show me and I may remember, involve me and I will learn," said Confucius. Maths and science contain many overlapping principles and many skills which complement each other. The national curriculum says that students should apply their mathematical knowledge to science. Maths is often the language that is used to record and display scientific phenomena truthfully. The cross-curricular approach, while attractive, does not come without its ideological, pedagogical, and organisational challenges. Teaching is a complex and more recently busy craft, and effective planning of taught lessons and collaboration between people is required if effective cross-curricular teaching is to be achieved. The cross-curricular approach has its origins in constructivism, which is not itself uncontested and not wrongly. Concerns about time, resources and expertise are an issue when implementing this approach. It is not without its merits, however, and can provide students with an engaging learning experience where key skills are applied usefully and effectively. Haylock remarks that primary teachers are unusually placed to be flexible to introduce mathematical approaches across the curriculum, and science provides a platform for this. How often has a student sat in a classroom and thought, what is the point of me learning this? What a cross-curricular environment does is to begin to answer that question, an approach backed by the national curriculum. Maths provides science with the means to analyse the truth. Integrating provides a basis for more stimulating learning. Moreover, an answer to that aforementioned question for students is seemingly, if not found, then given some opportunity to be developed. This is because a bigger picture is highlighted, where students see mathematics as forming processes, providing an understanding if coupled with real examples. This follows a constructivist approach that students learn through connections rather than discrete learning. A constructivist argument would veer away from rote and distinct learning towards veritable contexts, which help students to understand the world around them through the lens of mathematics and science. Additionally, it is stated that there are natural overlaps into each other and the real world, which are intuitively obvious, and further simultaneous learning. Students should be made to see mathematics as a mechanism to understand the tangible world. A cross-curricular approach gives accentuation to this approach. The skill set used and developed for both mathematics and science are similar and complementary. Essentially, cross-curricular is concerned with the ability for a teacher to use examples and data from a miscellany of disciplines to illustrate concepts and principles. The processes in mathematics and science are common and symbiotic, such as problem-solving, reasoning and proof, communication, connections, representation, engagement, exploration, explanation, elaboration and extension, and evaluation. Vocabulary used by these two disciplines is homogeneous, and therefore science and maths can be used together to develop and hone these skills, with processes often interchangeable if taught correctly, could be useful and beneficial pedagogical tools. Baxter says that there is a widespread agreement that mathematics and science should be integrated, although it is not clear what that looks like. Moreover, it is more likely that science will be used to teach mathematics, not vice versa. EMAS emphasises teaching in ways which accurately embody tools, processes, and difficulties with professional practice. That is not to say that this way of teaching is the ideal, or that it does not come without its issues, but the equivalent areas of procedure highlight that they could marry and be useful as teaching tools. Furthermore, Frickham and Glasson support this integration of vocabulary to promote different perceptions and practices of science and maths and their common context. How something is learned is part of what is learned, and science and math provide an exemplar for how to view the world authentically, where individuals are not passive. Often, teaching at primary level is geared towards SATs, as test results dominate the agenda for Ofsted. This means that subjects have tended to be taught discreetly in order to gear their students towards formal exams. The Rose Review was partly commissioned to address the concerns that the national curriculum was content-heavy and overloaded. The Rose Review attempted to view the curriculum as a whole, rather than treating subjects as distinct. This change is a constructivist one of learning by direct experience, not simple didactic teaching. Cross-curricular has a range of meanings, and no single identity can be assumed. However, it is a means of establishing links across science and mathematics. Hayes says that cross-curricular allows for investigations that engage and allow pupils to undertake active inquiry. Knowledge and skills in one area can be used to reinforce and expand knowledge and skills in other areas, allowing for a blending of ideas supporting the transfer of skills. Discreteness can artificially establish barriers. This was formative to the Rose Review. The fusing of subjects and applying them to real situations is a good way to make them applicable and valid to the learner. Moreover, we should not view maths and science as distinct disciplines that need mastering in isolation, but need to connect them synergistically and more efficiently and develop an insightful awareness of teaching ability. Of course, it is all very easy to say, but perhaps less easy to do. Central to effective learning and teaching is teachers' awareness of context and connections. While it is widely acknowledged that the cross-curricular approach is attractive, it is less efficient to implement. Teachers would need to do research. This is not always practical with an already busy job. Thus, time is needed to be granted to generate schemes. Moreover, this lack of content knowledge, or at least a feeling that content knowledge was insufficient, perhaps comes with it a lack of competence to try different activities or lessons. Although in Berlin and White 2012, teachers were recorded as having positive attitudes to the value of integration, with integration and collaboration seen as efficient. Primary teachers may have scant experience of scientific experiments and processes such as data handling. Additionally, it needs a willingness to try a non-discrete approach. Again, education is often aimed at performance in formal examinations, thus teachers will be cautious and discreetly hone skills. This is not the best approach, but it is a reality which should be taken into account. Moreover, when teachers try to do something, links made may not be the most natural or intuitive. Berlin and White say that knowledge is a social discourse, thus one way which subject knowledge concerns could be overcome is collaboration in planning between specialists. Collaboration planning could prove to be time, subject knowledge and resource effective if done correctly, overcoming barriers. Levels of integration differ, it must be noted. Therefore, when we talk about curricular integration, there is some confusion about what integration means, what it looks like and how it is actioned. Fogarty gives us 10 levels of integration, thus no one specification can be adopted. The range of integration is also modelled by Huntley. Further, it can be argued that learning needs clearly delineated boundaries, which should be said, Rose does not advocate elimination of. That is, rather than creating boundaries, teaching is clear and specific to the discipline. Primary school teachers need to show care of overgeneralizations and simplistic understanding. Fundamental skills are needed to implement the transferring of skills. There is also the argument that it is undemanding. However, it is also stated that situative learning provides a deeper or strong understanding, but the additional benefit is rarely specified. Thus, an interdisciplinary approach, where the distinct features remain clear, is perhaps the wisest of cross-curricular options. Epistemological issues must be taken into account. Science is by its complexion experimental and evidence-based. This can be seen at odds with maths, which is logical and can be seen as proof of knowledge. Thus, the pedagogical and organisational decisions need to be considered, as these two disciplines, despite showing some overlap, do need to be married to be taught effectively. Constructivist theory is also not uncontested. Kirchner says the practice of a profession is not the same as learning to practice the profession. Early learners should be provided with key concepts and procedures, that is, being guided in understanding before transferring. Alternatively, Melo Silva argue that learning environments must be similar to the context of use. It is also asserted that Kirchner's idea that content is substituted for practices is not correct. Haylock says that meaningful learning is the attempt to fathom experience by making connections, although there is dichotomy between the abstract and the concrete and how these interact. Lederman and Nice favour an interdisciplinary approach where discrete features are clear. There is a credible reasoning behind guided understanding as opposed to constructivist purism. Giving the tools and content to aid and embed learning through contextual scaffolds is one such suggestion. For instance, data handling is an overlap from maths into science and vice versa. Science as the context, with mathematics used for analysis of phenomena. Morrison and McDuffie show that pre-service teachers better understood data collection, among other things, by carrying out their own scientific experiments, and after having done it, they believed that they improved understanding for interpreting data representations. One participant was able to compare which graph was better to represent her findings. Here, mathematics and data handling was used to show and highlight scientific processes effectively. The teacher indicated that she would plan a similar activity for her teaching of mathematics as science, as it gives a model for developing data handling understanding, with her experience informing her. Data handling in the primary classroom can take form in various ways: planning science experiments or writing reports, storing and manipulating information in spreadsheets and creating graphs off those spreadsheets to analyse. Information is easily collated and presented if children are correctly primed. Centres like data loggers can be used to record phenomena and can be shown live on graphs using correct equipment and software, or using digital microscopes. Teachers can use interactive whiteboards to enhance their teaching to demonstrate examples. Pupils can use ICT for research purposes. Children can take photographs for recording or analysing, communicate findings with people from around the world, simulate or view scientific events, or showing information using presentation software. Children could use their mathematics skills to use a data logger to record information, a spreadsheet to collate and analyse that information, and then present their findings to the rest of the class using PowerPoint on an interactive whiteboard. This would use science, mathematics and ICT, which would be too difficult for a Key Stage 1 child, but they could do steps discreetly before they were able to complete the full cycle Key Stage 2. This type of activity would be a constructivist approach where learnt skills from mathematics are applied to another discipline. Care needs to be taken about the novelty of ICT's use, but if used fittingly, it could be a powerful tool in the expression of learning. Essentially, this is about equipping children with tools to be autonomous individuals in a difficult and unclear world. This is done partly through effective teaching, although not necessarily cross-curricular. However, cross-curricular teaching is effective because it makes links that are intuitive. Science and mathematics are effective to link because they are innate. While it has its constraints, time and ability to research and plan, resources and teachers' ability, these can be overcome. It seems that overcoming these issues is not simply the individual burden of the teacher. Time and resources, and it could be argued teaching ability, are often systematic. Teachers need to be invested in with time, energy and money if cross-curricular teaching is to be properly implemented. Of course, teachers bear much responsibility for this, but they are simply agents of a system. It is up to government and schools themselves to implement policies. That said, the potent inquiry skills that science provides us with is easily coupled with the intrinsically logical and truth-searching mathematics. ICT is an extension of these tools which, if used coherently, can only enrich learning and equip students for the modern world. The disciplines and their students deserve effective cross-curricular teaching.